NC State University is located in Raleigh, the capital of North Carolina and a major southeastern city only a few hours from the mountains, the coast, and the nation's capital, Washington, D.C. It's a vibrant city filled with arts and culture, natural beauty, great food, and southern charm. The area is also a fast-growing hub for technology and innovation, where top researchers and companies are solving the world's big problems in engineering and beyond. NC State is right in the middle of it all. We're a leading public research university with a long, rich history that helps us move boldly toward a better future. Here, more than 36,000 graduate and undergraduate students across many disciplines work together with expert faculty and top industry partners to think and do in new and exciting ways. Every day we're researching, learning, building, growing, collaborating, and helping society thrive. And we have fun while we do it. What can you think and do at NC State? Anything.
My name is Ayman Houari. I am Professor of Nuclear Engineering and Director of the Nuclear Reactor Program at North Carolina State University. We are standing here in the control room of the Pulsar reactor. The Pulsar is a 1 megawatt thermal power nuclear reactor facility. It was built in 1972, went critical at that time, and it's been in operation since then, almost 50 years of age for the Pulsar. The Pulsar is used for various activities, including supporting nuclear engineering classes, doing research using neutron and radiation beams, and also serving all kinds of users from the community and the industry, and also research organizations and government organizations by providing radiation facilities and radiation diagnostic facilities. What you see here is the control console of the Pulsar reactor. This is where our operators actually, on a day-to-day basis, monitor and operate the reactor, take it to different powers in order for the users to be given the type of radiation environments that they need and seek. The Pulsar is a reactor that is fueled with uranium-235 fuel that is in a UO2 form and enriched to about 4% or 6% in U-235 weight ratio. Also, it is cooled by light water, moderated by light water, and it's an open pool reactor facility where the core sits in a light water pool about 25 feet depth. The reactor itself is somewhat unique in that the moderator to fuel ratio of this reactor is almost 1, which really gives us a neutron environment where the thermal neutrons actually peak on the edges of the core, facilitating the type of utilization that we do in the Pulsar. The reactor is controlled by different control rods, and we can see here on the console the indicators for these control rods. The rods are made out of an alloy of cadmium and silver and indium, and this allows the operators to manipulate the power of the reactor and to make it reach a certain operational condition. We have an actively cooled core in that we have water being pumped in the core in order to make the core always stay at safe temperatures. The reactor has a primary cooling system connected to a secondary cooling system, and then eventually the heat is released to the environment. The core has several irradiation locations, like these standing pipes, where we can insert samples and irradiate them for different purposes. We also have the ability to introduce samples quickly and swiftly and remove them from the core through a rabbit tube system that allows us to pneumatically move those samples in and out of the core. We're also able to build facilities around the core over here for irradiation purposes. This reactor is also flexible in utilization because we can, as I said, manipulate the working conditions of the core in order to demonstrate various aspects of reactor operations. To give you an idea of the different facilities that we have established around the core of the reactor, and as you can see, this is the core again with the tube structures that I have discussed. This is a view of all of these instruments. We have instruments that can do neutron scattering on samples in order to study the structure of these samples at the micro and nanoscales. We have instruments that can do neutron imaging and radiography in order to see the internals of larger samples and, for example, examine them for any kind of defects and damage. And we have an instrument that is quite unique that is able of generating positive electrons. These are the positrons that interact with the samples and give us an idea of the defect structure in these samples. Because many times when samples are manufactured, you might have actual atoms that are removed from their positions and have defects in the samples that control the properties of the sample. We are now building a new facility around our reactor, which specifically aims at testing advanced nuclear fuel materials, looking at microspheres of fuels. And these microspheres then are studies in order to see how they behave under fission conditions. We also have a facility to look at fundamental nuclear physics aspects or neutron physics aspects. This is the ultra-cold neutron facility where we thermalize the neutrons to a very low energy at the nano electron volt scale, and then we are able to trap these neutrons and study their properties as free neutrons, such as the decay and lifetime of these neutrons. We are operating all these facilities simultaneously. Our staff scientists are able to operate, and also while other experiments and irradiations are taking place around the core itself.
This is our nuclear simulation lab at the Department of Nuclear Engineering. In this lab, we have this generic PWR simulator, which we use for our curriculum and research and outreach. So this GPWR simulator is a numerical model that models all the way from the reactor core to the turbine with the primary loop, secondary loop, and the safety systems. So it is a very important supplement to the simulation capabilities that we have in our program. In terms of teaching, we have incorporated this simulation lab, our simulator, into our nuclear reactor laboratory course, where we worked together with not only the pulsar reactor, which is the research reactor we have on campus, but also this numerical, full plant nuclear reactor simulator. And so students can have a full, complete experience of operation in a commercial nuclear power plant. We have been heavily using this GPWR simulator on our research side as well. More specifically, we have been using the simulator to generate a large amount of data to demonstrate the operation of commercial nuclear power plant. And those data is valuable for us to develop and train any machine learning models that could help us to determine the unseen pattern in the data, which will then be very useful for us to perform prognosis and diagnosis of the nuclear reactor systems.